So tonight we're going to be hearing a retrospect on the Voyager probes. It's Voyager 1 and Voyager 2, their epic journey. And Scott Marshall's going to tell you about what they've been doing in the last 10 to 15 years, because there's been a lot more happening than you would realise. So thanks very much, Scott.
Okay. Thank you very much, Wayne. And for those of you who have seen me give a couple of presentations, you know that I like talking about the history of NASA, because there are some incredible stories there that most of us don't know about. And some of the stories I've told with NASA are about the not only the people, but the technology that they've been able to put together. And this is another example of the amazing technology that they put together in the 1970s, 50 years ago, and still working relatively well for that 50 years. Now, just before I get started, as it happens, a few days ago, I was in the JP Morgan building near Town Hall Station in the city. And as I was going in the foyer, what hit me in the face, but a 5-metre sculpture of the Voyager probes hanging from the ceiling in JP Morgan. So that was a very pleasant surprise. Anyhow, on with the presentation. This is about the epic journey in several respects of Voyager and the team that put the probes together. The Voyager probes are still speeding through our space, as we know. Voyager 1 has journeyed more than 24 billion kilometres from Earth, while Voyager 2 has journeyed more than 21 billion kilometres. We're talking about technology put together in the 1970s. Both have been travelling longer than any other spacecraft. In 2012, Voyager 1 became the first spacecraft to cross from the solar system into interstellar space, which was a little bit loosely defined in those days, and they're still having a bit of trouble defining exactly what interstellar space is, but in 2012 it crossed the boundary. NASA has performed miracles to keep these spacecraft operational, and the journey is now about to end, very sadly. We pay tribute to this miracle of dedication, planning, design, and engineering. Just on the mission timeline, Voyager 1 launched in July 1977 and arrived at the interstellar medium in 2012, as I said. Voyager 2 also launched in 1977, just after. Voyager 2 targeted Jupiter and Saturn, then Uranus and Neptune as their core mission. The idea was to get that part of the mission under their belt, and then if things were still working, to go into what's called interstellar space. So it completed its primary mission in 1989 and is currently travelling at 15.3 kilometres per second. Kilometres per second relative to the Sun. And one of the primary contacts between Voyager and the Voyagers and NASA is through our very own Deep Space Centre near Canberra.
Scott, I'm so sorry to interrupt.
So a little bit of a timeline here. 1977, Voyager 1 launched, as I said, entered the asteroid belt soon after, still in 1977. And Voyager 1 overtook Voyager 2 in December 1977 as it measured in distance from the Sun, and exited the asteroid belt in 1978 without damage. Now remember, we're talking about a period where scientists were concerned that the asteroid belt was a little bit like out of Star Wars. Asteroids everywhere. Well, we've now flown a number of probes through the asteroid belt without damage. Star Wars isn't quite right.
Sorry, Scott, I'm very sorry.
In 1979, Voyager 1 started the Jupiter observation phase, and then the year after, the Saturn observation phase.
There are some people who aren't muted.
From those parts of the mission soon.
Listen.
And then after that, that was the core part, or the main part of Voyager's initial mission that was finished, and then entered the extended part of its mission, which was, let's just see how far we can push this through interstellar space. And they did a really good job. That's the extended mission that I'm talking about there. So in 1998, Voyager overtook Pioneer 10 as the most distant spacecraft from the Sun, and moving away from the Sun at roughly 1 astronomical unit, which is, of course, the distance from Earth to the Sun, per year, which is faster than Pioneer 10. So this spacecraft, 50 years old, and is traveling at one Earth orbit, if you like, per year away from the Sun. In 2004, passed the termination shock at 94 astronomical units from the Sun and entered the Helios sheath. Now, when we talk about the boundary between the solar system and interstellar space, there are a couple of boundaries, and I've got a picture coming up which shows those various boundaries that it's breaking through. Now, unfortunately, there were several systems that had to be shut down, not all of them because of failure, but because of the need to preserve power. The power system was designed to last until 2025, 2026, on the assumption that they shut various instruments down, which is what they've now done. And in 2012, as I said before, crossed the heliopause and entered interstellar space, becoming the first human-made object to exit the solar system. And unfortunately, I suppose you could say, since then, they've had to shut down further instruments on board the probe in order to save energy. So they terminated the ultraviolet spectrometer operations in 2016. In 2017, there was a trajectory correction maneuver where various thrusters were used for the first time since November 1980. So they had been turned off for that number of years. And when they were turned on again, they failed without issue. Sorry, they worked without issue. So again, it's the amazing technology that they put into the Voyager probes. Now, it wasn't all perfect, of course. You wouldn't expect it to be. There have been some issues with the onboard computers. And you've probably, if you go to podcasts, you'll see that the strange signals coming from Voyager, some of the memory chips started to fail. So they did have to basically turn off one computer, if you like, and turn on another that had been turned off years before in order to get around this memory chip failure issue. But apart from that, working very, very well. In 2025, in February this year, they turned off the cosmic ray subsystem as well. Now with Voyager 2, a very similar sort of timeline, again, launched in 1977 and entered the asteroid belt a few months later in the same year. So it doesn't take very long to get the asteroid belt. It's very close compared to where they are now. There was an issue with the primary radio receiver. That did fail on Voyager 2, but the remainder of the mission, luckily, was flown with the use of a backup system. Exited the asteroid belt in 1978 and then started the, let's call it the main part, the original part of Voyager 2's mission, which was to observe Jupiter and then Saturn. And remember, the extended part of the mission occurred after the primary part of the mission was completed. Started observing Uranus in 1985. Now, we're talking about a time period, remember, when we didn't know very much about these outer planets. I'm sure with a lot of you, when you think about Jupiter, Saturn, Uranus, there's a lot of imagery, there's a lot of facts, there's a lot of knowledge you have about these planets. Most of that wasn't known at this time. So it was Voyager and, of course, the telescopes we have today that gave us a lot of the information we take for granted, wasn't known in these days. The mission around Neptune started in 1989, and later that year, Voyager had finished its primary program and was starting its interstellar mission now. 20 years of a continuous operation in 1997 and 30 years in 2007. So this is really great timelines for this technology. Now, also with Voyager 2, to save energy, a number of the instruments had to be shut down. So there's a timeline here of, unfortunately, partial decommission of the probe. So the data tape recorder system was terminated, although it's still functioning perfectly at that time, no problems with it. The planetary radio astronomy experiment had to be terminated. There was a switch to backup thrusters to conserve power again. And then this probe crossed the heliopause in 2018, towards the end of 2018, and entered interstellar space. And then Voyager 2 in 2023, 2 years ago, overtook Pioneer 10. Now we're talking in distance here. We're not talking about physically passing it, but distance from the sun, to become the second farthest spacecraft from the sun. And as you see here, further instruments were turned off just recently to eke out a little bit more time out of this probe. Okay, so that's a very, very brief timeline. So what were the mission objectives? The primary mission was to explore the outer gas giant planets. And the secondary mission, as I said, was to explore the limits of the solar system and the interstellar space beyond the heliopause. The 1970s provided a rare planetary alignment that allowed a tour of the outer planets using the new concept of planetary assist. Now here again, we all know about planetary assist. It's second nature to us. Time of Voyager, they were playing with new concepts, new theories. It worked very well for them. And the timing of the launch was because the planets were aligned in such a way that you could get gravity assist on the way out to the outer reaches of the solar system. So Voyager 1's mission was to go past Jupiter, Saturn, and Titan. Voyager 2 was to go past Jupiter, Saturn, and then Uranus and Neptune, so we get a better idea of what these planets were. Now I've got two slides here showing the path of Voyager 1 and Voyager 2. And look, I won't leave the camera here, but the Voyager 1 track is the pink line going across the top of this diagram. Now this is plan view, sorry, of the solar system. So you've got the orbits of the various planets. Plan view, Voyager 1 coming across, let's call it the top for this diagram, and Voyager 2 being the blue line coming more towards the bottom, and Pioneer 10 that we've been talking about is the orangey red line going through the middle there. Now that's plan view. We can also look in, let's call it sectional view, if I could use that term for the solar system. And you can see that Voyager 1 is going upward. Now, I hate to use these terms, but this is just colloquial expressions. It's going up while Voyager 2 is going down, and Pioneer 10 you can see going through the middle there. So that puts the various orbits into perspective for these probes. Now the power system. I said that some of the, well, most of the instruments now have been turned off to conserve power. Each Voyager is equipped with 3 multi-100-watt radioisotope thermoelectric generators, RTGs, and each RTG includes 24 pressed plutonium oxide spheres. At launch, each RTG provided enough heat to generate approximately 157 watts of electrical power. 157 watts is not a lot. Collectively, the RTG supplied the spacecraft with 470 watts at launch, but being radioactive, that energy halved every 88 years. They were predicted to allow operations to continue to at least 2020 and continue to provide power to 5 scientific instruments through the early part of 2023. In April 2023, JPL began using a reservoir of backup power intended for an on-board safety mechanism. As a result, all 5 instruments have been expected to continue operations through 2026. So that's the drop-dead date, if you like, for these probes. In October 2024, NASA announced that the plasma science instrument had been turned off, again preserving power for the remaining 4 instruments. The various instruments on the probes when they were launched, and I've got here listed whether those systems are still active or have been turned off. So there's an imaging science system, a radio science system, infrared interferometer and radiometer, all those disabled, as has been the ultraviolet spectrometer. We still have the magnetometer in operation. Most of the rest have also been disabled: the plasma spectrometer, the low energy charged particle instrument, cosmic ray system, planetary radio astronomy investigation system. The photopolarimeter, unfortunately, is defective. Not everything survived, and the plasma wave subsystem is still in operation. This is a bit of a diagram to show where the various instruments are on the probe. I won't go through all this in detail, but you can see here where those instruments are located. The thrusters for the probes, it's via a single 70 centimetre diameter spherical titanium tank. It launch contained 100 kilograms of hydrazine, providing enough fuel until 2034. So there's enough fuel there, just not enough power. A summary of the key achievements. Importantly, Voyager followed Pioneer 10 to photograph and measure the outer planets. Voyager also analysed the heliopause boundary and, just as important, managed to survive for almost 50 years in the tough space conditions due to the dedication and ingenuity of the JPL engineers. Now, that's very, very important. A couple of the talks that I gave previously about the Apollo program highlighted the importance of the people in the program that made Apollo successful. It's the same with the Voyager mission. And unfortunately, one of the senior engineers, the guy who was actually in charge of Voyager and also was in charge of half a dozen other key NASA projects to the moon and through the solar system, passed away just 2 or 3 weeks ago. But he was absolutely instrumental in making this mission a success. So it's not just the technology, it's the people as well. Cassini, John Cassini, is his name. Yeah, he passed away 2 or 3 weeks ago. And sorry, it says here that he was the project manager for Ranger, Mariner, Galileo, the Cassini probe, Voyager, you name it. He was a guy in charge of all of those. Okay, so the small blue dot. I'm sure we've all heard of the small blue dot. And you've probably all seen photos of the small blue dot. Well, I think a lot of those photos are actually colour enhanced. This is the small blue dot without any enhancement. This is where Voyager was told to turn around and take a photo of planet Earth. And this is actually one of the, although you can't see anything, it's actually one of the most important photos taken. And the reason for that is because of what Carl Sagan wrote about that photo. The following excerpt from Carl Sagan's book, Pale Blue Dot, was inspired by an image taken at Carl Sagan's suggestion by Voyager 1 on the 14th of February 1990. As the spacecraft was departing our planetary neighbourhood for the fringes of the solar system, it turned around for one last look at its home planet. Voyager 1 was about 6.4 billion kilometres away and approximately 32 degrees above the ecliptic plane when it captured this portrait of our world. Caught in the centre of scattered light rays, Earth appears as a tiny dot of light, a crescent only 0.12 pixels in size. So that's why you can't see it. It's 0.12 pixels in size. But look again at that dot. Now this is what Carl Sagan wrote, okay? Look again at that dot. That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there on a mote of dust suspended in a sunbeam. The Earth is a very small stage in a vast cosmic arena. Think of the rivers and blood spilled by those generals and emperors, so that in glory and triumph they could become the momentary masters of a fraction of a dot. Think of the endless cruelties visited by the inhabitants of one corner of this pixel on the scarcely indistinguishable inhabitants of some other corner. How frequent their misunderstandings, how eager they are to kill one another, how fervent their hatreds, our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help would come from elsewhere to save us from ourselves. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. So that really drives home the point that it doesn't matter what the megalomaniacs think they should be doing, it has zero consequence when you look back at it. Now, Voyager didn't take just a photo of Earth at that time. It also scanned across and took photos of the other planets in the solar system. So this is its camera scanning across the solar system from that vantage point. And these are the other planets that it took photos of. Not very detailed photos, of course. There's Jupiter, there's Earth, Venus, Saturn, Neptune, Uranus. They're all in that montage there. Okay, the gold record. You've probably all heard about this as well. This was affixed to both of the probes. And this was a way for us humans to potentially communicate with somebody else if someone's lucky enough to find this probe. I'll give you some numbers on that in a sec. So this is the gold record. And you can see some etchings on this, which are explained in a slide coming up, which explains exactly how to play this record to get the information that's embedded on it. Both Voyager probes had the gold record attached to them. The Voyager golden record contains 116 images and a variety of sounds. The items for the record were selected by NASA, chaired by Carl Sagan of Cornell University. Included are natural sounds, including some made by animals, musical selections, spoken greetings in 59 languages, some human sounds like footsteps and laughter, a printed message from President Jimmy Carter and UN Secretary General. Now, it's actually a fairly detailed etching on this gold record. There's information here on where the probes were sent from. So this is pulsars and the distances from the various pulsars, so you can see where the sun is. There's information on how to play the disc. So this is sort of like an LP. That head, I'm sorry for the people online, this head is actually within the probe. So if you take the head out, you can then play the disc. And there's information here on what the recording should look like, the waveforms, and other information, including a scale here in hydrogen atoms, to help explain how to play the disc. So if you're intelligent, you might just get through all of that. These are some photos that were taken. Remember, these are the first times that humanity got a close-up view of these planets. Most of these planets. So this is pictures of Jupiter and some of the moons, Saturn and some of the moons. Now, because this is color enhanced, but you can see the detail in the rings that wasn't apparent beforehand. Uranus again, and some of the moons. Uranus, unfortunately, hasn't got a lot of detail, but some good photos of the moons here as well. And Neptune. Again, Neptune doesn't have a lot of detail, but there's bits and pieces there that are of use. A summary of the mission results. First of all, Voyager 1. Photographed Jupiter from January 1979. Most detailed photos of Jupiter, its rings and moons occurred over 48 hours of closest approach around March the 5th. The photographic mission of Jupiter ended in April of 1979. Discovered rings around Jupiter. Discovered volcanic activity on the moon Io. Discovered volcanic activity on other moons. And notice that dust from the Io volcanoes is located between Io and Jupiter. So the dust left the moon and is now located between the moon and Jupiter, and potentially raining down on Jupiter as well. Saturn, closest approach occurred on November 12, 1980. And the probe detected complex structures in the rings of Saturn. And that was quite exciting. I remember reading about that at the time. Measured less helium than expected in the upper atmosphere, 7% compared to 11% expected. So this is where the probes were testing some of the scientific theories, which were based on incomplete data, but then helped the scientists build and fine-tune their models. Might suggest that heat generation from helium as it sinks through the hydrogen atmosphere, explaining why Saturn radiates heat. So one of the potential sources of heat with Saturn. Measured the length of day as 10 hours, 39 minutes on Saturn. So key, elementary, but key information. And measured Titan's atmosphere by directing communication signals through the atmosphere of Titan towards planet Earth. And the results of that indicate lakes of hydrocarbons on Titan. The interstellar part of Voyager 1's mission in February 1990, Voyager 1 took the family portrait photos of planets in the solar system. The camera software was then removed. The cameras are no longer operational after that photo was taken. I've already mentioned overtaking Pioneer. Now Voyager 1 is currently traveling away from the sun at around 1 light year per 18,000 years, if you want to use that as a measurement of speed. And entered the termination shock around the solar system in December 2004. In March 2011, Voyager 1 was commanded to do a 70-degree roll to observe the path of solar wind at the termination shock. So this is Voyager 1 trying to take a bit of an angled view, if you like, of that termination shock to get more data on what's actually happening at that point or at that zone. In December 2011, detected Lyman alpha radiation from the Milky Way galaxy. And in December 2011 also entered what's known as cosmic purgatory, where cosmic radiation from the sun's energy is turned back on itself from the force of energy coming from outside the solar system towards the solar system. And that was a distance of 113 AUs, astronomical units, from the sun. So 113 times the average distance of the Earth from the sun. I'll skip all that bit. Some recent technical problems. Okay, it hasn't all been plain sailing. You wouldn't expect that with a piece of hardware 50 years old, especially in the cosmic radiation situation out in space. So in May 2022, this is recent, Voyager was transmitting peculiar telemetric data. The attitude, articulation and control system was functional, i.e. the spacecraft was oriented correctly, but telemetry data coming back to Earth was corrupted. The problem was found to be that the AACS, the Attitude Articulation and Control System, was using the wrong computer for communications, and that was fixed. In November 2023, Voyager 1 started transmitting data that was unreadable. Flight data subsystem may have been struck by a high energy particle or simply failed due to age. Data transmission is now okay because NASA now avoids that damaged computer chip within the computer via some reprogramming. And in October 24, the X-band transmitter used to communicate with Earth was shut down via Voyager's fault detection system after NASA turned on a heater unit. It switched to the S-band transmitter until the X-band transmitter could be reactivated. So what appears to have happened is when that heater was turned back on again, NASA detected that as being a fault within the system and shut a few things down. So NASA then had to go in and tell Voyager, no, it wasn't a fault, we just turned the heater on and now things are okay. Voyager 2, the closest approach to Jupiter, was at a distance of 570,000 kilometres above the clouds. The Great Red Spot was analysed and other red spots were identified in that time period. There were 9 volcanic eruptions that were recorded on Io and confirmed some linear features, some cracks on Europa's surface. Now, those cracks are now common photos, but they weren't known at the time. And also identified 3 new satellites around Jupiter. Around Saturn, Voyager 2 measured Saturn's atmospheric temperature and pressure by directing communications, again, through the atmosphere towards Earth. And then the distortion of the signal was used to measure the atmospheric conditions. And we do that a lot now anyhow. The scan platform malfunctioned at Saturn, and the fix was not perfect, unfortunately, which meant that they missed the flyby of Titan. A small miss for this project. But successfully was able to do a gravitational assist and moved to Uranus's orbit and went past Uranus. At Uranus, the closest approach was just over 81,000 kilometres above the clouds. Discovered 11 new satellites around Uranus. Also started to study the unique atmospheric conditions caused by the 97-degree axis tilt. So remember, Uranus is pretty much on its side. Discovered that the magnetic field is not aligned with the rotation of the planet. So that was new to the scientists, and there's ongoing investigation there. A few other things here. What else? Of those, I think the last one is the important one, identified 2 rings around Uranus. So most of these large gas giants actually have rings around them, not just Saturn. Around Neptune, observed 60 lightning flashes and 16 electromagnetic wave flashes while in that short period going past Neptune. Again, identified rings around Neptune. They all have rings. Located 6 new moons and saw the great dark spot, which has since disappeared. It's like the red spot on Jupiter. They wax and wane over time. And then into the interstellar part of the mission, after they finished with the gas giants in the outer part of the solar system, in August of 2007, Voyager 2 passed through the termination shock about 1 billion kilometres closer than Voyager 1. The heliosphere is not symmetric in both solar system hemispheres. So remember, one went north of the ecliptic, one went south, and they've discovered that this zone around the solar system where the impact of the sun's rays is not a perfect sphere around the sun because of the nature of the external forces on the solar system. In April 2010, there were some computer glitches with Voyager 2 as well, prevented data being transmitted. And this was fixed again, well, this is by resetting a memory bit rather than bypassing a failed memory bit. So this is just NASA getting around the fact that the computers are getting old. Reached interstellar space in December 2018, about 2 years later than estimated. And in 2020 encountered a significant increase in the density of space. Now, density of space out here is a bit of a relative term, but an increase in the density of space. Now, that's still something that's been investigated with Voyager as they come right to the end of their life. They are still sending back information, and this is one of the things that they're looking at still. What's causing this? So it's interaction of the sun's rays with the various cosmic rays and other energy coming from the rest of the galaxy and elsewhere, and impacting with the, let's call it loosely, a sphere around the sun, and it's that interzone where it's interesting things happening. Okay, so this is just diagrammatic of where the probes are and have come from. Obviously, we've got the Earth here, third planet out. We have the heliosphere. Okay, that's the sun's territory, if you like. And I've used terms heliopause and termination shock. They are indicated there by the white arrows, showing you let's call it the gradation of influence of the sun as you go further and further away from the sun, and you get more and more influence from energy from outside the solar system. The Voyagers are where the red arrow is, so you can see just going through the heliopause there, and they've yet to enter the Oort cloud. That'll be an interesting experience for them. Not a dense group of rock, asteroids, etc., but an awful lot of it distance-wise. So we'll just see how they get through the Oort cloud. Again, like I won't go through a lot of detail here, but Voyager 2, same story as Voyager 1. Great technology, lasted a long time, but because power was running down, they progressively turned off the scientific instruments that they didn't need in the position where the Voyager now is. So you can see each of these experiments being progressively shut down. And if the Voyagers were to last longer, if you look at the last two lines here, 2030, there will be no power, so there will not be enough power to power any of the instruments, 2030. And in 2036, they'll be out of range of the Deep Space Network of Canberra anyhow, so you won't be able to communicate with them. We're not going to get there, unfortunately, with these probes. The mission conclusion. NASA has had to prioritise which instruments to keep on and which to turn off due to the diminishing power. Heaters and other spacecraft systems have been turned off one by one. The fields and particles instruments that are the most likely to send back key data about the heliosphere and interstellar space have been prioritised to keep operating. Now, this is what I said. This is a new part of space where we haven't had probes before. We're really not quite sure what's out there. So the instruments that are useful for measuring the heliopause and the energy in that area, they've been left on as long as possible so we can get the last bit of data out of these probes. Engineers expect the spacecraft to continue operating at least one science instrument until I got here around 2025, so around about now. And as we know, unfortunately, it's probably more than just the power system that's going to determine the end date for these probes. Voyager 1, some thrusters needed to control the attitude of the spacecraft, and Pointer's high gain antenna in the direction of Earth are out of use due to clogging problems in their hydrazine lines. Another issue. In September 2024, so only a few months ago, NASA performed a thruster swap, switching from the clogged set of thrusters to less clogged ones that had not been used since 2018. In May 2025, the team was able to revive the backup thrusters used for roll motion that were unusable since 2004. So these are bits of equipment, rockets, that hadn't been used for 20 odd years, 2004 in this case, and still work perfectly. So that's great to see. Okay, so what happens at the end of these missions? Well, Voyager 1 is expected to reach the Oort cloud in about 300 years and take about 30,000 years to pass through it. In about 40,000 years, it'll pass within 1.6 light years of the star, however you pronounce this, Gliese 445, at 17.1 light years from Earth. So only have to wait 40,000 years. And in 300,000 years, it'll pass within less than 1 light year of TYC 3135. So if anyone's around then, watch out for this. Okay, so Voyager 2 is not headed towards any particular star. The nearest star is 4.2 light years away, and at its current speed, the spacecraft travels 1 light year in 19,500 years, during which time the nearby stars will also, of course, have moved substantially. In roughly 42,000 years, Voyager 2 will pass the star Ross 248, which is 10.3 light years away, at a distance of 1.7 light years from that star. So when we're talking about passing by a star, we're talking about at a distance of 1.7 light years. If undisturbed for 300,000 years, Voyager 2 should pass by the star Sirius at a distance of 4.3 light years. So almost close enough to ask for a cup of tea.
Is that accounting, is that if they were to continue on the speed that they are now, or is that accounting for the fact that it gets the half-life?
Okay, look, there's a lot of things happening. One is that the sun still has a gravitational influence on these probes, not very much, just a little bit. And then also, of course, you're going through the Oort cloud, who knows what you're going to encounter or come near as you go through there, which will just skew you a little bit. And there may be other things, could be a stray planet, because we do know that planets after a supernova can leave their solar system and they're sort of stray through the galaxy. I think James Webb has seen one, I'm not sure. So there's all sorts of things that can just deviate it. So this is just assuming constant speed, constant direction. Yeah. Okay. The expected final year or so of communicating with the Voyager probes is now in doubt. Unfortunately, if the Trump administration is successful with the cuts to NASA, contact with Voyager will end very soon as the Voyager team is disbanded and the communications equipment is turned off. Unfortunately, a real possibility. However, there is an alternate future for Voyagers. It could return as a Voyager to its birthplace, the planet Earth, and we all know about Voyager from Star Trek. So that's one possible future for it. And well, thank you very much for listening to my presentation on Voyager.
That was fabulous.
Any questions? And don't make them too technical, please. So why the decision to direct the two craft above and below the plane of the eclipse? Oh, because as I said, the heliopause is not a perfect sphere. So they just wanted to see what the distortion was and what could have caused that. And they have discovered that it's not a perfect sphere. Did that impede the flybys of the other planets? No. I won't go back to the slides, but yes, the gravitational assist was basically within the ecliptic of the solar system, so they could get to the planets and then use the last planet in each of their missions just so the thrusters just sort of send them like up high, if you like, and please, I'm using the colloquial terms, so that when they went past the last planet in their mission, the gravitational assist would just shoot them down or shoot them up.
A couple of questions, Scott. Do you want me to read them out to you?
I've got one more for him. I think it was David. I think
we'll do the.
Yeah.
Well, I just thank you for that presentation. I just got a quick question. You went to termination shock a few times. What is that? What, I mean, the shock is quite a provocative word. What happens there?
Oh, well.
You want me to answer?
Yeah, go for it, Because there's different sorts of ends or near ends of the influence of the sun's energy and what happens there. But I'll ask Ivor to answer that question in better detail than I could.
Well, I mean, the termination shock is, you've seen them in the sink every so often. When you've let water come down from the tap into the sink, and then it's extended out usually in a wave going outwards. That rolling wave, as it goes out and then eventually knocks into the edge of the sink and comes back, that's like the termination shock. The basic thing is that the solar wind is traveling supersonically, and actually synchronically, but let's say supersonically. The local interstellar medium is moving very slowly. And so there has to be a shock transition to basically slow down the solar wind so that it can now interact with the local interstellar medium. Having said that, plasmas or ionized gases with magnetic fields in them, a little bit like oil and water. One plasma with its magnetic field does not want to mix easily with another plasma with its own magnetic field. So the solar wind coming out from the sun, moving out, it has the magnetic field induced at the sun. It does not like the idea of mixing with the interstellar plasma and magnetic field. And so the heliopause is the boundary that separates those two plasmas. And so the solar wind plasma comes out, it's slowed down at the termination shock and deflected a bit. And as it goes out further towards the nose, or the direction in which the solar system is traveling, it gets slowed down and then deflected around the outside, so that it stays inside sort of heliopause. And on the outer boundary, you've got the heliopause, and that's where you start to see the interstellar plasma. And as Scott said, you see changes in the magnetic field, changes in the density, changes in the cosmic rays. And really that's the evidence that we've crossed the heliopause, is that the density changes by about a factor of 10, according to data from the plasma wave subsystem, or PWS. You see changes in the magnetic field as well. And you also see a change in the cosmic rays. Basically, the cosmic rays, most of them, are excluded from the solar system. They're kept out in the interstellar medium. Now, it could be that there's an outer bow shock because the solar system is moving at about 23 kilometers a second relative to the local interstellar medium. And that's just on the boundary of being supersonic, according to our current measurements. We're not sure whether there's an outer bow shock. And if there's an outer bow shock, then we expect another shock transition there, and we'd be seeing denser plasma where we are, or the Voyagers, than is actually in the pure interstellar medium. I think most of us believe that there's no shock, that it's right on that boundary, and we're actually now seeing density structures that you mentioned, Scott, where I can't illustrate it properly. You didn't show the most important picture. No, the density structures. But I mean, basically, the density as you go out from the sun, it goes down 1 over distance squared. get the shock transition, the termination shock goes up by a factor of 4. And then it starts to decrease again, then it goes up by a factor of 10 at the heliopause. And then it was going down again, and then we've seen this increase again by a factor of 1.5, 2, something like that. Does it keep going? No, we're not sure. So it's finally
But
poised.
the plasma instruments are off now, aren't they?
Oh, the most important instruments, the plasma wave subsystem,
Oh, that
which is on. And the reason it's good is because when you get a shock wave traveling from the sun via coronal mass ejection, etc., some of those, not all, but some of them manage to cross the heliopause and move out. And it's sort of like a blast wave. Just moves out, and as it goes, it can reflect electrons and accelerate them. You can get these lovely waves that I like studying called linear waves, and you can get the density from the frequency of those waves. And that's what a number of us have been doing for a while.
And do you remember how many watts the transmitter has? It's minuscule. Yeah, I was thinking of what 1 point something watts. Yeah, so
Not very much.
yeah,
And at one level, it's jolly annoying because you look at that power, 170 watts, and most of the important stuff is scientific instruments, and that's less than 5 watts. Where they are wasting all their time.
The only reason,
Yes,
the only reason we can still hear it is because the gain of the antenna
oh yeah,
is 60 dB.
yes.
Yeah, we have to use radio astronomy dishes.
Yeah.
We have to use dishes tens of
I just find it amazing. I recognise all of that, but I still find it amazing that something a 1 watt transmitter and you can pick it up.
It's worth noticing the total power of radio emissions observed on Earth on all of the astronomical, etc., radio telescopes, much less than 1 watt.
And where's all the study that you're doing? Where do you do all of the study that you're doing? Or
At the University of Sydney, but in my case, I'm collaborating with Bill Kirk, who's at the University of Iowa, who's now the principal investigator of plasma wave subsystem. And many years ago, I met my better half there at Iowa, and Don Burnett was the original principal investigator of PWS, but he died last year. Because everyone's basically, well, all of the older ones anyway, are shuffling off this mortal coil.
They've passed it down to students.
Well,
So what-
that's right.
question up. Never mind.
No, I'm a theorist, really, but so Bill's the person who's relevant, and I think there's a
Well,
person
that's
called,
longer than for the,
I think the next likely person is Alison James.
but it sounds like it's not gonna make it.
No, I must admit, I think Bill believes it's a bit longer than 1 year. I think he's expecting 2 years or so, but well, the Trumpy, will do what Trumpy wants, but NASA's very keen to keep the Voyagers going because it is their data is utterly unique, and humankind is not going to get another probe out there for a substantial time. Even New Horizons, which you had your figure, Scott, which had the trajectory.
Oh yeah, there's a couple of probes on that. Yes,
Me one.
yes.
New Horizons is somewhere near 80 AU per month. So not beyond the termination shock. But if it gets there, then it will have real plasma science instruments. No, it's half. Yeah, but maybe it's only at 60
It's
AU.
faster. I thought New Horizons was faster.
I don't think so. I think Voyager 1 is traveling fast.
And so that it was maneuverable as well, I think, because they planned to send it out to Pluto and then they were like, oh, and now we can do this, we can do that. Yeah.
So it's mostly again traveling in a straight line, pretty much. Just a very slightly curved line that's gone past a couple of asteroids.
And I'm not sure, but my guess with New Horizons, I'm thinking of the Nancy Roman telescope that I talked about a couple of months ago. One of the things I picked up from that was the technology on that is an advancement on the James Webb, in as much as the James Webb telescope was a test bed, if you like, for the Nancy Roman. And I wonder whether the same thing is sort of happening with New Horizons, where, okay, you've got probes out there, we've got a bit of an idea of what's happening. So those instruments could be designed for not.
New Horizons was primarily designed for Pluto.
Okay.
Certainly the plasma instrument was designed for Pluto, but with the hope that NASA would keep funding them so that they could get to interstellar space, or at least to the termination shock. So yes, it's a vastly improved plasma instrument, and the magnetometer is fine. Magnetometers are pretty boring in one sense, but the plasma instrument is a real plasma instrument.
One of the things I picked.
No plasma.
One of the things that I picked up when I was doing research for this was the scientists on the Voyager project. They first had a lot of trouble sort of getting all the funding and everything that they wanted. That just happens with NASA. So they made the decision amongst themselves to have the probe designed so that it would last well beyond the funding timeframe. So the funding timeframe was basically the four gas giants, basically. And they said, okay, we'll do that, but everything is designed for a longer timeframe. So it was a dedication of these guys, their vision, their love for the project, everything, like the Apollo mission, gave us what we have today.
I think really in this case it's Ed Stone who was the principal. He was the original project scientist on Voyager, who got everyone behind that idea. But of course, you know, it was all sotto voce. I mean, the NASA people knew, but it's something you don't mention.
Yes.
That this is what we're going to do. We're going to design it so it lasts those very uncertain radiation environments in Jupiter and Saturn, and have plenty of power because, you know, we might need that power to send out signals. And if it happens to last, well, you know, we've got that grand tour and that trajectory. But yeah, I think it's really Ed Stone who made that happen.
Sorry, Ray.
A couple of questions. It's a question about why the Voyagers didn't go to Pluto.
I haven't read a reason for that. I'm going to guess because the mission was the four gas giants. Oh, and also, don't forget, you can only go somewhere if it's on the path.
That's right. No, we didn't line up because Pluto's orbit is quite different to the other.
Yeah, that's right. So it's not on the path that it's going.
That's the main reason.
Yeah, yeah.
They couldn't even get anywhere near.
That's right.
There was a hope that New Horizons might be able to go to more than a few.
And I don't know the exact number, but it was something like almost 1 in a century alignment of the planets that they were very, very lucky. Not Pluto.
Not Pluto.
No. Yeah.
It's more just that it's in a different phase.
Yeah.
That's the issue. It wasn't in the right location.
Yeah.
They needed to get the gravity assist to keep going towards, you might call it, in the direction of rotation of the planets around the solar system. Pluto was just not in the right place.
Yeah.
Or very good flagging.
The period is very long. Orbital period.
Yeah. And also don't forget, of course, that Pluto is sometimes above the ecliptic and sometimes down, so it's very, very hard to get to it.
New Horizons.
Sorry, Wayne?
Another question, were there any backup plans if the gravity assist trajectories didn't work as intended?
I don't think there could be a backup because they didn't have enough thrusters, hydrazine, so it was just, that's it. Yeah, that's right. That's right. That's right.
It was quite amazing. I happened to be in the team for the Neptune encounter. So I was at JPL for it with part of Don Garnett's team. And, you know, we were coming in pretty much the ecliptic and getting towards where we expected rings to be if there were. We didn't know for sure, we didn't know for sure that there were rings. But we needed to go through that area of space so as to be able to get close enough to the moon, whose name I've forgotten at the moment, to do the gravity assist to go southwards. And we could just see the counts of hits on the spacecraft, where you get a lovely electric field signature. And so we could see in the plasma wave data the hits and us moving in the ring plane. Will we get through or not? And there was a data gap just closest to the edge. So we're going ping, 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 ping. It's getting louder and louder, more and more hits, and the data gap. And then it was something like 5 minutes, if not 10, before we knew whether we'd got through. And that was a huge. I don't know how many heartbeats we missed, but it looked like quite a few. So it was, I mean, it's really the tour of the unknown. In each planet, you know, we saw things which were hugely different than expected, whether it was the rings and the associated dust, whether it's, you know, the enhanced radiation environment, although that was probably known from the pioneers for Jupiter and Saturn. But then Uranus and Neptune were totally different, you know, as you said, Scott, on their side, both of them, but the magnetic field not aligned with the rotation pole. Totally unexpected. It's a totally different model where the magnetic field comes from. So it's been an incredible tour, and you know, the scientific and I'd call it the social benefits of that mission have been incalculable.